Does anybody have any requests to start with? I don't have my any particular thing on my agenda right now. So anybody got a type of problem or a specific problem from either anywhere, actually. So this is not going to work. Oops. And now it's really messed up. I think I'm going to do that. Now let me see. Great. Engineering. Anybody? Bueller? Anything? Anybody want to go, oh, you know what problem I would like to see? I would like this kind of problem. You just want me to start talking? Just randomly pick something out? A bunch of problems. Okay, a bunch of problems. That sounds good. All right, let's talk about what we've covered so far since exam 1. That's a good place to start. Let's see, what did we do? Oh, we did deflection. And underneath that was superposition of various kinds of deflection. We also had some buckling. Then we had static failure theories. I got static failure theories. So this was chapter 4. And static failure theories was chapter 5. And let's see, the first thing we covered were safety factors and statistics. We covered stress concentration factors. Distortion energy theory, von Mises, maximum shear stress theory, brittle Coulomb-Moore, and fraction of Coulomb. So those are like the big topics, right? That we would typically cover. But also types of problems. As always, door handles, 3D shafts, and pressure vessels. So the application of these things to those things is kind of like our main thing, right? The main kind of stuff that we covered. Some of them were like, we zoomed in and we did some specific things, like, for stress concentrations. We just like, we'll just make it a specific stress concentration. Or we might make it with a door handle, right? And we might make it with distortion energy theory with a stress concentration and a door handle, right? Or 3D shaft with maximum shear stress theory. Or a pressure vessel with maximum shear stress theory. Or brittle Coulomb-Moore with a stress concentration in a door handle. Right? Those are the kind of general things that you could be looking for with a problem. And I think I'm going to try to avoid using the problems that are in the packet so that you have those for practice. So that means that I have to wing it and come up with a new problem to be able to do. And that's always kind of a little, a wee bit dangerous, but whatever. So I might pick one we haven't done. So I think we haven't covered this problem right. Let's see, we did this one in a review session, didn't we? That guy?
Oh, here's drawings.
Here's two door handles that are new to the Shigley. Want to pick one of them? Yeah, this guy right here. Is that the right? I don't get my left and my right mixed up. You said, do you want to do this guy? Sure. Let's do him. So this would be problem 355 out of the book, but I'm sure if you look in chapter 5, they probably refer to it somewhere and say, let's see, trying to be quick about it, but look for problem 355 mentioned somewhere. Is clevis pin. Yeah, I don't see it. A lot of times they'll do that though. They'll reuse the problem because of what we call laziness. Yeah, whatever. Let's invent a stress concentration to put on there too. All right. So here's the basic problem rewritten out. Here we have that thing. And we have loads upon it of 200 pounds. Load coming this way of 60 pounds. And a load coming up of 75 pounds. And, oh, there's also a load right here of 300 pounds. Dimensions. This thing is 0.75 diameter. And this is 5 inches. This is 6 inches. Decided to use this symbol for inches. This distance, hard to tell. 5.5 inches. I know it's got a messed up dimensioning there. And I think we're okay. This is A and B, C, and D. And just to make our lives more complicated, let's pick one that we haven't done. And did they tell us the material? They didn't tell us the material here, right? Because we're not in that section yet. But we're going to go with, let's see. We'll pick the lowest one here. We'll pick our 1006, excuse me, and make him hot rolled. Right? So 1006 hot rolled. So we're going to have a yield strength of 24 KSI. This is cheap steel. Ultimate strength of 43. I don't think we need that, but maybe it's good to know. And let's take a stress concentration of this. Oh, I don't know. And we only have 2 choices really with the round ones. I guess we could do a hole in it, but that just messes everything up. I guess we have 3. And we'll just make it so that it's, actually, here's one that we use sometimes. we'll use the idea of this right here, but we'll say it's up into the wall, so the fillet is like, right in there, if you understand what I mean. So, where normally we have a D over D, and we have to look up a D over D and use one of the lines from the D over D. Right, we'll have to use one of those lines. But this gets done pretty often where, okay, the capital D is now infinite. So what Shigley does in many different problems is they just use the largest one they have. D over D is 3. So I guess infinity equals 3. And, therefore, right? That's their mindset. But it's the best one they have. So instead of like extrapolating, I don't know what you do for extrapolation of that. But that's what they would do. All right. So we're going to pretend like there is a, I don't know. We'll go in the middle of the road. Well, we'll just see here in a second. I'll when we get to that. So our first thing that we want to do is, first thing we want to do is to get the loads that are going to be at this section. And we're no longer looking at a particular spot, right? We're no longer looking at a particular element. We just want to find out when this thing's going to fail. So we need to have the moments in all of the directions, right? So this is X. I think we could have predicted that. That's Y. And I think that's parallel. That's Z right there. So we start off with some FBDs. I think I'm going to go in my FBD. I don't have to be color coded. Go right in there. And so looking at this, actually you have to be careful. These are kind of like on top of each other. So we have that 300 right up there. And we have our, nope, let's go down. And we'll have our 75 right there, and our 300. We also have an axial of 60, and that 200 doesn't show up anyway. So we'll have like reactions that direction, and I should have made this clear, X, Y direction first. And that one's going down, so we're going to have a reaction that goes up here. That's R, Y. And then the moment, yeah, this one's going to go clockwise, so this is probably going counterclockwise. Here's our reaction moment about the Z-axis. And this thing's 5.5 long. So we'll take a sum of the moments, take it about the Z-axis, and we could just subtract this in our head, right? The 300 minus 75, say 225 MRZ is the reaction we want to go, and this is going to be, so we have 225 times our 5.5. I wish I brought my real calculator instead of my.
You're not going to promote that.
What's that?
You're not going to promote the calculator app.
Oh, the calculator app. Oh, yeah. Well, I got my free, the free 42, right? We have the free 42. It's just I like the physical calculator better than this one here. Although this was actually performing better because I spilled like coffee on my. So sometimes the keys stick. So if I make any mistakes, I just blame the coffee stuck keys on the Hewlett Packard 42. And I don't have a 42S. I can't remember. The other one, it's just slightly different, but it's better. Hewlett Packard calculator. You need to switch to that. It becomes real intimate. So you get the MRZ equal to 1,238, call it, inch pounds. Let's see. it that way. So next free body diagram, oh, let's look at the top of the thing. That's sort of an exciting one right there. Call it an FBD. Say which direction. Oh, did I just do it? No, I did it right. Okay. So this is the XZ plane that we're looking at here. And forces, forces, forces. We have 200 pounds. And we have 60 pounds. And I don't think we can see anybody else. Both the 300 and the 75 are into the board. So our reactions in the X direction, our Rx is this, and our RZ is that. And our moment, let's see, that one's going counterclockwise, that one's going counterclockwise. Our reaction here in about the Y-axis must be going clockwise. And any dimensions we need, this is the 5 inches. And here, this is again 5.5 inches. Anything else? No, I don't think so. So we could figure, we don't even need to write out some of the forces. I didn't do it over here either. Maybe, I mean, we could already see that RY should be 225. But we do want to do some of the moments about the Y-axis. And so we got a negative, what we've drawn. And then we're going to have a positive 200 times our 5.5. And then positive 60 times our 5 equals 0. So MRY. $200, 5.5 times, so you get 1,160 times 5. Should be able to do it in my head, but I'm not gonna. I think it's 300, right? Yeah, it is. So you get 1,400 inch-pounds. And then the last FBD is going to be in the YZ. YYZ, anybody know what that is? Anybody? Come on. Oh, you're hurting me. You're killing me. Anybody know what YYZ is? First off, it's the airport code for Toronto Airport. But it's also a instrumental by the band Rush. It's a Canadian band. Look into it, please. So sad. Sorry, I'm sorry, Geddy Lee, and Neil Peart, and Alex Lifeson. And are you familiar with Rush? And okay, so the reason why that particular thing that you might want to know, what makes it interesting in YYZ is the rhythm to YYZ is the Morse code for the letters YYZ. I'm going to get it wrong. Never mind. Not a drummer. And so our reactions, which don't look we have a reaction here in our RY and our Z. That's what the Brits call Z, by the way. And they're very, very, very adamant about it. So this is going to be counterclockwise. So I didn't draw that very. Let's see. I'll erase some of it. So I can get my arrowhead somewhere. I can see it right there. Didn't do a great job. This is our MRX. Right in there. You be neater than me. That's do as I say now. It's like, no, that's not good. Anyway, let's see. So our reaction at X is that direction, but we're going to have 75, and we didn't put on the dimensions. And we can say this 5 inches. So 5 inches. So our MRX is 75 times 5. I should be able to do it in my head too, but anyway, 375 inch pounds. We should really just stop now and listen to YYZ. No, that's not a good use of our time. But I kind of want to hear it anyway. Do you think it's on my phone? Okay. YYZ? No? Just we could listen to it. No, it's going to make it. I guess we can't. I have to actually have YouTube up there. Moving on. YYZ. We can listen to it just for a little while it's there. It's often, is it often moving pictures? Oh, it's got 2 advertisements, so we listen to 2 of them. So there you go. We can listen to it while we do this. All right, now we need, this is equal to torque. By the way, this big flag when I post this up on YouTube for copyright because they're going to hear that music on it, so that's great. Well, I just can't monetize this. They don't need to look at it. So we're going to have the moment. We want the maximum moment, bending moment. Let's take the square root of this one and that one. So now you know YYZ. I wasn't just making something up. Now I could never play this because it requires way too much memorization. I don't like memorizing this. Now I got to use my calculator, so this has to turn off. So I know. It's sad. That's why I should have the other calculator. We should play every class should be to music. The music in the background. That would just contribute to the chaos, right? And we just need more of that. That sounds reasonable. 1,869. Can they see that? Oh, that's really far away. I don't know how small that is on the computer screen. Yeah, when I picked this room, I was like, oh, I use this room. Okay, that's good, because I forgot that it doesn't have so I had to use stuff on the board. Okay, so we know the torque, we got the loads out of the way. Now we might want to do, because we decided that we're going to have a fillet. So I need a fillet radius on here. I'm not in the screen right there. So I want to pick something out of here that makes sense. So I'm probably going to go reverse engineer it here and try to pick one that it seems reasonable to me. I guess I'm going to go with an R over D of 1.5, just arbitrarily, just because it's in the center. So whatever that radius is required with 0.75, right? So 0.75, and we can work backwards. And so what is that? We divide. Trying to think here. R over D. So I multiply 0.15 by 0.75, and so my R is going to be.
I have a question.
0.1125. Right, that's what I picked, so that my R over D is 0.15. And for my big D over little d, like we said, we're going to pick 3. No, wait, we're just going to pick the biggest one. They're different in each of these, unfortunately. So we're going to pick the biggest one. So 4. I could write it here. Axial. KT is approximately I'm looking at it upside down. It's somewhere between 1.6 and 1.8. Did I hear 1.7?
That's what I said.
1.7.
Gold.
So, bending, which is kind of weird because they go axial torsion and bending, so it's easy to accidentally go to the center one when you mean this one. You just be on the lookout for doing that mistake. I make it all the time. We're using big D over little d. Oh, that almost comes out exactly 1.6, huh?
I have a
That's
question.
nice. Check that one out, Gracie.
I have a question.
Focus, hold the book steady, then. Almost exactly 1.6. So. And you would expect these to be this really close to each other. It's really the same kind of stress. I mean, you know, you zoom in onto the thing, it doesn't really know the difference between axial and bending. It still looks kind of the same to the thing. And then lastly, for torsion, or torque, that's a TS. And we're going to be approximately, and we have to use D over D of 2. And I say it's going to be, let's see, that's 1.2 there. I say it's going to be 1.35. Hold that kind of steady. What's this one? 1.35, because 1.3 is in between that 1.2 and that 1.4, but it's still kind of hanging up. I don't know. Getting up there. So, we use our nominal. We could have done this in the beginning. It really is like a dance. I'm trying to do these little hybrid things. I need the area pi over 4.75 squared. Uh, 0.4418 inches squared. Pi over 64.75 raised to the fourth. Classic mistakes always are. Well, actually, I usually don't. I usually just give this because it takes up time, right? I'm always running out of time. Did I get that right? I don't know. I don't feel like I got that right. No, I got it right. Okay. 0.75 raised to the fourth is only 0.25. That's not what I got. Yes. All right. I'll go 1.227 e minus 2 inches fourth, and j is just going to be 2 times I, so 2 times that, or 2.454 e to the minus 2 inches fourth. So now we'll go for now. I guess I could do this in one step. I don't have to necessarily calculate the, so I can get the sigma x, and I'm going to combine, because this is going to be in tension, right? The force on here, the only thing creating axial is that 60 pounds. So we're going to choose tension for the bending as well. If that were compression, we'd choose compression, you know, just to make it the largest we could magnitude. So I could do this KT F over A plus KT, and I might make this, I might like over here, but you can't see it now. Right? Oh no, I guess you can kind of see it. You can comma A and comma B right there. So that when I get over to here, I can make them specific. Comma A, comma B, MC over I. So 1.7, 60, pretty boring. They're not going to be a very large number. 0.4418 plus 1.6 in our 1869, 0.75 over 2. Divide that all by 1.227.
I got something different for I. I did as well.
Okay, what did I get wrong?
0.0155.
All right, so that's gonna be around 2, right? So what did I do? 0.754. Oh, I know what I did. It's never mind.
Back swipe it.
No, it's the Y to the X is actually a sub key onto the thing. So I should have hit the orange button before I hit the thing. I'm used to my other calculator that is an actual button, not a sub button. I just looked at it really quickly. That's why you might even see me. I took 0.75 and then I took 4 and then all right. You said it was 1.5?
1.55.
And then 2 times it. Okay. So that's the 3.106 e to minus 2. And so you got 1.55, 3 e to minus 2. And numbers. And 0.375, 1.6 times. So this is up getting, already getting 36,000, like for that part of it. And 60 divided by 0.4418 divided in 1.7 times. Yeah, this one right here, this is barely anything. So this comes out to 36.33 KSI. You probably picked the wrong material over there. The torsion onto this is going to be our KTS TR over J. So 1.35. And our torque probably, it's not really all that much, right, compared to just 375. Much smaller than our bending moment. So this is probably not going to be a whole lot. 375.375 times and 3.106 divided 1.35 times. To get like 6.112 KSI. Yeah, I got the same thing twice, so. Okay. Von Mises is easy. Okay, so we have
We got
Unix.
something a little different.
You did?
Yeah, for the bending moment.
For the bending moment?
Bring down the whole X, right? We got 72.3.
Really? Wow. That's huge.
That's how you do it.
Oh, yeah. Must have hit 72 point something. Thank you. Well, that's good. Really, that thing's really going to break. It'll fly up in space. I don't even need to actually calculate this one. Just to double check it. But 1.7 times it. I'm going to change it 72.44.
Yeah, roughly, yeah.
And so that's on the tension side. And looking on this thing, let's see, can I go that way? So actually the torque is coming this way. So if we're looking down on the thing, I think we're going to have it go that way. So we got our 72.44 KSI at some spot that's along the X, but we don't know where it is this way because we took it in two different planes, right? And 6.112 KSI. And so the von Mises is the easier one to do. Let's see this, right? Sigma x plus 3 times tau squared. We'll call it xy, but it's really not. So that's the 72.44 squared plus 3 times 6.112 squared, 1/2. So in our von Mises, let's see, can I do this? Sure, squared, and then flip them, and square them, multiply by 3, add them, square root them. I get 73.21. Yep. So if we wanted just to go for our distortion energy theory safety factor, we take SY divided by von Mises, and we have a ridiculously small safety factor because I didn't anticipate the stress being this high. Well, we did put the stress concentration on there, but 24,000. So I get it's going to be 0.33. And at least in my class, I insist that we don't use more than 2 decimal places because there's no real point to it. It's already failed. So giving you more on there doesn't really tell you much more than. If we want maximum shear stress theory, because it's uniaxial, we can skip doing more circle. All right. Well, we could always skip doing more circle, but it's just a good idea to use it. But we can't just go directly to an equation, and I think I have it memorized. Maybe that the tau abs max for a uniaxial is just going to be the x divided by 2 and the tau squared. Yep. Right? Yep. It's not fair to be cramming all this into the thing down at the bottom corner, but I guess. 72.44 divided by 2 squared plus my 6.112 squared. Get tau abs max. And I squared it. I think I squared it. 6.112 squared. Add it. Square root it. Doesn't come up to too much different. 36.73 KSI. So my maximum shear stress theory is SY divided by 2 divided by tau abs max. So 24 divided by 2 divided by 36.73. And I get 0.33 is that one too. It's slightly lower, but not with only 2 decimal places. But that's really hard to read over there. I guess maybe you can see it. How are the people on the home front doing here? Where are the 2 diameters on the example to use for KT and K charts? Okay, but that was a question for a little while ago. In this particular case, what we're and this is like a common thing that happens, Jemai, if you can hear me. I'll double check that you can hear me. Right? Still got the microphone going. We're still recording. Okay. Sometimes if you have a situation where you're right up against a wall or something, or something very large, they do this with gears as well when we try to get the stress concentration, because the tooth you could think of as a cantilever beam. Spoiler alert, that's for ME370. But it's like the capital D out of our stress concentration is huge compared to the little one. So you just what you end up doing is just use the biggest D over D that you can for that chart. That's that's what I decided to do instead of just to pick out a diameter, because this thing is drawn up as if it's up against the wall. So any questions on any of that? It's kind of fairly, it's stuff we didn't really add that much to what we had covered in exam 1.
Assuming we're not going to be doing any graphical stuff on the exam.
I have done it before, but I don't know if I'm certain that that's the most, like, what am I measuring, right? I try to measure, mastery of the material. Are you able to graph something on a little graph? I don't know. It was mostly, making that part of the assignment to kind of like give us, comparison and contrast between these, but also setting it up for the real Coulomb more and kind of seeing it. We're also, trying to justify myself here. I don't know if I told you. Do I sound like I'm making excuses? Yeah, no. You're going to see in a little bit with fatigue, they do some more of that idea of being on a boundary and doing a graphical approach to try to see how far something is either inside or outside of a limit of a boundary that you draw, right? So that's one of my mindsets in like, okay, well, I'll have them graph this because that's the same concept that we keep going on with fatigue. All right, so let's want to pick another problem. We did a little bit of stress concentration. We did distortion energy theory right here. We did it there. By the way, you see what I did right here? Yeah. Do that in every course, right before your exam, right as you're doing your exam prep. This is some of the secret to my success. I'd go through every homework problem that we did, and I'd try to organize it and try to see. And then when I went to prepare for an exam, I tried to make sure that I did a couple problems that used all of these things. I would check those off as I'm going through. Have I mastered that? And then I did, and by the way, did it even in graduate school, because you just won't believe how unorganized some classes could possibly be, and you're going to be expected to organize your brain, right? So organized approach to test taking can really, really help it. I can't tell you how many students I see that when I ask them a question, I could almost like read their minds and see how disorganized all the jumble of information is. Like, well, but it's in there somewhere. It's just getting a hold of it when you need it is tough because there's just so much going on. So organize, 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 and that includes your brain. And actually, a little bit literally. It's almost a physical kind of nature to the way your brain works, where things are stored and that kind of thing. All right, so deflection. We don't want to do that one in deflection. But I have asked problems before that were deflection problems that didn't require any calculation. All right, and I would be like, name the different sources of deflection in a part. All right, and maybe I mean that's it. Write down the equation you would use. All right, so you don't have to put any numerical thing on top of it, but you go, oh wait, that thing's bending in this direction. Right? So we could actually use that same problem right here and just try to list them out. Because once again, I like numeric problems, but I also, my main goal is to, in testing, is to measure your mastery of the topic. Like, have you absorbed, processed, and built the skills to be able to like solve the thing? So now I got to retry. I won't be as neat. That's what I'll do. Save time. I'll be less neat. You don't know. I probably can't do it. Can I? I'm probably gonna just some OCD thing. How can you be like? I asked this question before. How can you be ADD and OCD at the same time? Is that possible? And I was told it's possible. It was actually one of my coworkers that said it to me. You're OCD. I'm like, that's not true. How hurtful is that? So we got to pick let's pick a location and pick a direction. Like if we're going to say, like we wouldn't want to say every direction. So let's say, well, Y is probably the one that we use for like our default direction that we want to go. And so let's take a look at point C. That's this guy. Deflection of C in the Y direction. Who contributes to it? So one of the first ones I might go to, my natural inclination was to go with torsion. So how is torsion going to affect point C? Well, who's causing torsion? That's a good question. 75 pounds, right? So without any, I'll write the 75 pounds, right? Causes torque. I don't know how to write this the best way possible. So maybe I should try to think that through as I'm right here. Causes a twist, right? And that twist, that's an easy one to remember because it kind of over TL over JG. So the deflection of C in the Y direction is really going to be theta. That theta is going to be, I'm going to say it's about the X direction, right? So it's a twist that's going around that direction times that length right there, which is, did I say this is B? Is B in the middle? B is in the middle. So that's times LBC. And that's going to be in the negative direction. All right, what other kinds of things might cause? Well, I picked a weird one for the Y direction in C. That might not have been the greatest one.
Three is also the 300 is also.
It is, but not by a torsion, right?
Right.
What kind of, how is it gonna make a C go down?
Bending on the shaft.
Yeah, so bending between A and B, right? So, and maybe I should write of AB, bending of AB, and it's really going to be the 75 and the 300, right? So I just didn't have a name for them, so I'm using the numbers. Causing a moment about the z-axis. This is going to cause deflection, and we might want to look up that equation. I mean, it depends how how I ask the thing. Sometimes I like ask the so that's really going to be case 1 out of this. I don't know why I'm holding my thumb in there. It's going to be case 1. With forces at the end of the thing. So, and it's going to be the forces at the end. So it's going to be F, L, and maybe I'll be specific and say it's AB cubed over 3EI. I can even be specific that it's because these things are different shapes. It's actually AI. I mean AB. AB. I don't know if there's going to be too much more. We don't have that kind of scenario where there's like some of the ones out of the other planes. Let me think about that. No, I don't think that 60 is going to do anything. The 60 can't do anything to affect the y direction. It affects the x direction in 2 ways. Right? One would be that it would be axial. Technically, that's a really small amount. But it would also be because it would be creating a bending moment about y that would move this in the negative x direction. And that one would actually be because of the slope of this, right? So even though this would bend between, this is D right here, this would bend BD, that would not cause any deflection at C in the Z direction. But the moment that was placed on here at that location right there would tend to bend AB itself. And then you would take that slope, and that means this guy would be going backwards. You'd be going into the board because of the slope at the end of AB. Trying to think of any others, or that would be the x direction. Yeah, and the z direction at C, that would just be the bending. Yeah, that would just be the bending of B, and B would be moving. The moment about Y would create bend in that direction, and that would make that go in that direction, same distance as G.
Would the 60 also impact the deflection in the Z direction of C?
Let me think. Yes, yes. And that too, yeah, that too would be, both that 60 and that 200 would be making it go about it. You too. Hopefully this is helpful.
Would the 60 put it in the Z direction or negative X?
Well, it's going to independent. I mean, it's going to do both things, right? I mean, but you have to concentrate on one particular deflection and at a time, as opposed to. It's better to look at the deflection that you're trying to find and then see what all the causes are, as opposed to seeing what all the causes and forces are. In my opinion, if you're going to organize your way methodically, go through the thing. Do one or the other maybe, and not both, because you might double dip. Is that good enough for a deflection like overview kind of thing? I tend to not like ask the numeric question because there's just opportunities to make little numeric mistakes, and and so everybody's gonna have the number wrong. So then I just have to go through and try to figure out where they got. So to try to communicate somehow that that you understand the different sources.
What pages, what are those formulas on?
That's it's in table A9, and in the 11th edition, it's 1029 is where they start. And that concept that we're doing right here is superposition, right? That we're going to have that the individual deflections all add together to get the total deflection is a case of superposition. All right, so another type of problem.
H21 for pressure vessel, chemical refining.
Okay. I just made my computer on my table under superposition. All right, so let's take a look at a pressure vessel type of problem. These ones, there's not a lot in Shibley, unfortunately. Right? So I invent one, so which are dangerous, so dangerous. So pressure vessels lend themselves to maximum shear stress theory problems because they're the kind that will generate a 3D Moore circle and not be uniaxial stress. So well, one of the problems I had on exam 1, I had a pressure vessel hanging from the hooks for some reason. And it had a big old weight on the bottom of it for some reason. And some young punk probably came around and decided to twist it for some reason. So I put a little pressure gauge on here. So arbitrarily picking out parameters here. Let's say that this thing is, I don't know, 36 inches in diameter. I'd give you the height of the thing, but it don't matter. But I might give you the height just in case you think it matters. That's kind of mean, a little mean. I'll say the thickness of the thing. Well, we want it to be thin walls because nobody's got time to do with the longer equation of the thing. So I think 1/8 of an inch is going to be pretty small. Yeah, it doesn't even sound like it's going to survive this. The weight that we're going to hang off of the thing, sometimes I'll pick the weight, like I purposely went backwards onto the thing and said, I'm going to make it more, I wanted to flip-flop the longitudinal and the hoop stress. So, because the longitudinal stress adds with the axial that gets caused by the weight. So I kind of like made them, I don't know, just to amuse myself. I don't know, not to amuse myself. I just see if I could do it. And I was like, oh yeah, I did. But the weight was like stupid big, right? So I made the weight like, let's make them 10,000 pounds. This is also probably going to be stupid numbers. So I make them in Excel. I set the problems up in Excel, and then I go, what if? And I change the numbers back and forth. I'll mess around with it. And then the torque, just so I could make them significant with each other, because otherwise you pick out a number and it didn't even matter that you put it onto it. Let's say 25,000 inch-pounds that we place onto this. And it doesn't matter where the stress element goes. Right here. And by the way, if I was a bastard, which I'm not saying I'm not, I would tell you what the strain is right here, just to be a jerk. And then you wouldn't need any of this other stuff. And you'd be able to figure out what the stress was and then do the maximum shear stress theory for it. That'd be a total red herring. It just occurred to me to do it. But I won't do it. Hey, next year. You're going to watch this old video that we'll post, right? The next class has to put up with that nasty idea I just came to my mind. Because we didn't do strain in this year. We haven't done strain since exam 1, so why the hell would I ever want to need to know that ever again? But can you reach back into the past and recover those memories and try to figure the thing out? Wouldn't be that hard to do. It would be faster to be a strain gauge that you had to transform. Now that, because you don't even have those equations in your book, right? So that's just jerk central.
That'd be one of those times you ask you why should I know that, right?
Why should I know? Why would I? Because you took my class and you remember everything you did. I can even hear my son sometimes just in a very joking way, jerk. That's right. All right. I didn't say what the pressure was. 1,000 psi. Okay. So one thing that we probably would provide for you was the cross-sectional area of this. Maybe I also want to figure out and see the radius. The outside radius of the thing is 18 inches. So the inside radius is just the radius minus the thickness, or it's a 17.875. So this is really going to be wicked thin. So it's T over R. I can do either 1.125 divided by 18. You know that's going to be less than. Yeah, it's going to be crazy. I just did this reverse. Yeah. So what is that? 6.944 e to the minus 3. Yeah, thin walled, which is less than 0.1 thin. I hope they can see that at home. Those playing home nutrition.
So we always use the outside radius.
Use it, but either one. Either one. If it's in between, toss a coin. I don't know whether you do the thin wall, but generally speaking, that would be. Yeah, we could go ahead and use thin. If you check both of them. But let me think about that. Yeah, sure. No, I agree. It's a good question. But in the practical side of things, if it's 0.0001, go with 20. So okay, I did this. So for the so also the diameter, I don't need the outside diameter necessarily. But 17.875. You know that's I could have done it in my head. 35.75. Yeah. So pi over 4. That'll be dO squared minus di squared. So I'm going to have 18 squared. No, I don't. I mean 36 squared. 36 and 35.75 squared, and subtract them and multiply by pi and divide by 4. Now I get this is 14.09 inches squared. So I could just get my axial stress. F over A. So that's going to be the weight of 10,000 pounds divided by 14.09. So actually not even that much, huh? So this is only 709.8 psi. Tension. So I should have made this thing like way bigger. I'm not buying that up there. I'm trying it out. 36 squared and 35.75 squared. I subtracted them. And then I multiplied. No, that sounds right. Okay. I've got the same thing then. Okay. Very small. Let's see. I'll go with the hoop. The tangential there. And that's going to be P di divided by 2t. So 1,000 psi times my diameter, which is inside diameter, 35.75. And this is on the outside surface, we decided, I guess. 2 and 0.125. So 35.75, 1,000, 2 divided 0.1255. Woo! 140. Did I get that right? 143 KSI. Oh, I got it. Oh. Whee! That was very, very thin. This axial didn't matter a damn bit. Because the longitudinal. So maybe we want to go ahead and make that to 100. There you go. We fixed it. And the hoop is really obviously just half of that. So, wait, I still had this wrong, didn't I? Somehow I had that. What the hell did I do?
That goes up to 100. It should be 14.3 KSI.
It should be 14?
Yeah. You multiply by 10. So you made the pressure 10,000 instead of 100.
I got you.
As far as the math.
Okay. So am I okay with this is 7.15?
Yep.
All right. And then lastly, this torsion. I don't know how badly we did here. We have to do a J for that. That's kind of a pain. That's pi over 32. DO fourth minus DI fourth. Just sort of a pain to make a G fourth. But we got 36 and raise it to the 4. And the 35.75. Yeah, 75. Raise it to the 4th. Subtract them. It's a big number still. All right. I don't know if we have enough of a torsion that's going to matter, but let's see. Did I just get done? It doesn't seem right. I got like 4,533. That's
Nice.
yeah. Wow. That's huge.
Wacky numbers.
Yeah, yeah. So we might have to really increase that to make it worth our while. So you have my 25,000 inch-pounds. Doesn't seem like a lot compared to, and so we have 18 inches. This is our R, and our crazy 4,500. Nah, maybe it's gonna be okay. All right, so we're gonna go 25,000. Multiplied by 18. Oh, no, it's actually really big. That's 99. No, it's not. No. This is 99 PSI, right?
Yep.
That's wimpy. Even if we made that 250,000, that's still pretty small compared to the other thing. Let's do it anyway. So 992.7 PSI. So we put all these things together into a stress thingy. Element. That was the word I was looking for. Stress element. Oh, we're not covering everything up here. I'm sorry. Home version of the game. So anyway, this is what a 0.9 F1927 KSI. And the direction, let's see, going that way, so this would be arrowheads in that direction. The hoop is this one. And this one is going to be the 7.15 plus 0.7098. So we're going to get 7.86. So now we really should do a more circle. I've been using purple a lot. I'll switch colors. Purple is a very educational color. Brown, not as much. Say again? Encyclopedia brown. We already knew everything. And nobody uses encyclopedias anymore. That's sad. Encyclopedia salespeople just didn't go through. They're not their own luck. All right, so let's see. We get like a four. Let's call that around 14, and that's around the 7 or thereabouts. And that's going to be up here and there. The center right here, we'll call that the R. Make our circle here, so I got C first. C is going to be our 14.30 plus our 7.860 divided by 2. 14.3 and 7.86 divided by 2. I get 11.08. And then our R, let's see, I could already draw what this is going to look like there. Kind of sad. Oops. Oh, pretty darn warped right there. I don't think I made it with that. Our R in this case, I'm going to say we want this leg right here. So I'm going to take C and subtract out the 7.860 squared. Well, in my tau is the meager 0.9927 squared. The glare is really going to mess with you up there. I don't know if that glare is off this. No, the glares are from coming through the okay. So minus our 7.86 and squared and 0.9927 squared plus square root. And it's going to do much. Did you get 3? Anybody doing this? 3.370? Yep. So then our sigma A, which is actually going to be equal to our sigma 1, is going to be C plus R. 11.0. So add them. You get 14.45. Sigma B, we don't actually need sigma B here, but that's going to be sigma 2. I guess I'll call it sigma 1. That's how abs max up at the top. I should do this over to the side because I'm standing right in front of the camera. I'm never going to make it in Hollywood. C minus R. That's 11.08 minus our 3.37, and so we have 7.71 KSI. But the really important one is the tau abs max, which is sigma 1 minus sigma 3 divided by 2. That's a sigma 3. It doesn't look like a 3. But sigma 3 is 0 here. So we're really just taking 14.45 divided by 2. And getting 7.225 KSI. And we never said what material it is, but let's just, as everything Dr. Deal with is in love with A36 steel, right? So we know that that has a yield strength of 36 KSI. And so the maximum shear stress theory safety factor is that yield strength divided by 2 and tau abs max. So 36 divided by 2 divided by 7.225. So that's 18 divided by that. So you get a 2.49 safety factor. We're kind of covering safety factors. Kind of have pressure vessels. There's another just maximum shear stress theory. Oh, we did on time, 225. Let's check in with the home team. How did you get 7.860?
I have that question.
Oh, my bad. I didn't write it out. That's how I got it. Maybe we ought to put this back on. No, never. So I should have. Sigma y was the sigma longitudinal plus the sigma axial, which was 7.15 and 0.7098, right? Because this is actually PSI. Yeah. Okay. So I should have written it down. I left the stuff out. You should write it down on your exam, right? Just skip a thing like I do. Something distracting. Some bright and shiny was floating through my head, I think. Yeah. I was thinking about YYZ again. So like at the Merchant Marine Academy, they like to torture you when you're a freshman. I don't know, because someone tortured them. That's not a good way to live, personally, I think. Just because something was lousy was done to you, they're going to treat other people lousy. That's the opposite of the golden rule, right? We had to sit at tables, right? You had to sit at like about 10 people to a table during meals. And you were required as a freshman to, especially at the beginning, you had to sit on the edge of your seat and look down at the edge of the top of your plate. And you were like, you had to put your fork down every time you ate something. And then they were the seniors, and then everybody that wasn't a freshman got to ask you questions, and you had to stand up and sound off and say your name and what company you were in. And you can answer the question, but there's only like 3 acceptable non-answers. To yes sir, no sir, and I'll find out sir, right? Or you would answer the question directly. So they had a lot of plead knowledge that you had to memorize, and sometimes it'd be like the hometown of different officers in the Corps, and that kind of thing. The latitude and longitude of the flagpole, and all the history of the flagpole, the height of the things. They're very obsessed with this flagpole. It was a Nazi flagpole. I want to point that out. It was like confiscated, but it was the tallest unguided flagpole, and or it was, I don't know. Anyway, people loved to mess with that flagpole and always getting in trouble for it. Like people wanted to paint it. Some people, there was a big eagle at the top of it. I always thought it was a Nazi eagle, but I never know for sure. But they want to get tires, like they would grab and put tires. It's all kinds of things. But anyway, I said the company commander stayed with Chris Church, and he would always ask him when there was music playing during the thing, and he'd ask him, Mr. Deal, sir, Kennedy Deal, push copy, sir. Says, what band is playing right now? And I didn't listen to much rock growing up. And what I did listen to was not, I didn't listen, there wasn't anything on the radio, so it was just whatever friends had and that kind of thing. It was almost always Rush. So I never heard any Rush, never heard of them, didn't know. I mean, I saw my friends last weekend. I'm like, I didn't ask them this time, but I've asked them before. Didn't we listen to Rush? When they're like, nah, not really. No, they did, but I never did. But anyway, I took to like, so the answer had to be, I'll find out. So you couldn't say, I don't know. That was the big thing. I'll say, I don't know. I'll find out. He says, well, then go find out. And then he made me go. I'd have to go up to the place where they play the music and find out, and then they come back down. Rush, sir. But without fail, he'd be asking me about this. That was how I know about Rush, is that they would ask me all that stuff. So do I resent them? And that's why I don't listen to Rush. No, it's because Geddy Lee's voice is awful. I mean, it is just terrible. With this guy's voice, it's terrible. I'm not. Okay, what kind of song we want to do? Now we had a little Rush break right there. I do admire them, just don't like listening to them. What kind of problem we want to do? Let's see, we want to do a 3D shot from. Everybody loves them so much.
Wait, what about the DE26? Will you find that for this too?
Oh, for this one too? Yeah. So the equation that I would use for the distortion energy theory for this one, we have a choice. All right. So looking that up, I have the one that's memorized, but I actually kind of have the other ones memorized. But since we found the principal stresses already, it might be infinitesimally quicker, not really, but maybe just a itty tiny bit, little quicker to use. See if I can get this in there. This equation, this equation with the principal stresses, right? Because we have both principal stresses. Or if we didn't have principal stresses, this is the one we would go to, right there. Because it has, it's not uniaxial stress. But of course, I'm all fond of the uniaxial stress equation, which isn't in the book. I don't know why, but it's easier to memorize. So,
Sigma B, sigma 2, or sigma 3?
sigma A and sigma B are the two non-zero principal stresses.
Okay.
In the event that we were to have principal stresses, we would need to use the only equation we can use for that is this one right there. All right. All the other ones are just simplifications of that equation, that main guy right there. So without room to use the thing, I would say that for my von Mises stress, I would take, I'm not going to write out the equation, I'll put the thing in there instead. I would use this guy right here. I'd say 14.30 squared minus 14.30 times 7.860 plus 7.860 squared plus 3 times 0.9927 squared, square root of that whole thing. That's really hard to see for the people at home. Sorry. That's a lot of calculator work. A lot of opportunities to type that in. 7.860 squared plus 1.9927 squared times 3 plus square root, and maybe I got it right, I don't know. 12.52 KSI. So we have the DET of our yield strength 36 divided by 12.52. I get 2.87. Which, I mean, I might have made a calculator error there somewhere.
I mean, that's what I got.
Oh, good.
I did plane stress and I got the same thing.
Oh, cool. Awesome. All right. Wonderful 3D shaft problems. Holy love it. And I say 3D shaft problem, that might be a 2D shaft problem. It's only so much time that you have. One thing I had considered doing was asking more questions. Okay, so one thing I probably will never try ever again because it just fails. I'm terrible at them. I'm terrible at taking them. I'm terrible at writing them. Is multiple choice questions. I just hate them. I hate them with a passion, and I think I overthink them, but I still, even overthinking them, I still make these like errors where like, oh yeah, the phrasing of that is ambiguous. Shoot, like that. Because it's one of those exercises in empathy in some respects because you need to put yourself in all the audiences that could possibly be, in all the ways they could possibly misinterpret what you're asking, and even the answers sometimes, like, oh wow, either one of those. Well, I guess from a certain point of view, I guess that one also could be true. I hate that. So I try not to, but I have thought about, explain maximum shear stress theory to me. Like, why do we divide the yield strength by 2? And a sarcastic answer is probably going down the right track. Apples to apples. I mean, I say this phrase over and over again to the point of being a little ridiculous, right? And just keep repeating the same thing. Why is that? I ask, and no one responds. And at some point, I think you'll be trained by the end of the semester. You'll say apples to apples.
I mean, if you put anything like that on the exam, I'm saying apples to apples.
There you go. And then if you were in my fluid mechanics class, you'd say Bernoulli. The answer to almost every question I ever ask, and when I taught fluid mechanics, is just Bernoulli. And got to the point where people would just answer that even when that's not, they knew that wasn't the answer to the question. All right, so let's take a simple one because we have about 24-ish minutes left. They only have so many problems in here. I'm always on the lookout for more from other books. I don't know if I've used up. So I'm trying not to be indecisive, but it's so easy. I think I've used up most of these. I don't think I've ever used this guy. That one right there. He's almost 2D, but he is still 3D. But the nature of the problem, what they're trying to ask right in here, is they're combining a chain here with a gear here. And they're telling you that that gear is producing a force that's coming down that way at an angle of, let's see, it's usually 20 degrees, but yeah, 20 degrees. And for lack of a better thing, I think we're going to go to FC. They don't even put it on there what that thing is. Other dimensions, let's see, this is 250 millimeters. And this is 75 millimeters. I'm going to leave the millimeters off. 250 millimeters and 125 millimeters. And let's see, did they tell us? Yeah, okay, so this thing's diameter, I guess his dB is 150 millimeters. They kind of showed over to them. It's actually like right in there that they're telling us that that's the in-between chains where they're telling us that. Oh, and they're also being clever. Little jerks, aren't they? So in their cleverness, didn't see that. They're telling us that this diameter is 125 millimeters, and they did draw in a shaft up here, and they're saying there's a torque right there, and I bet they're giving us that torque. I gotta read it carefully. Maybe I should have picked one that would go faster. But I didn't. It's 100 meters. And okay, let's see, other things that we need to know out of this. Assume no frictional losses. All right. So in order to maneuver through this, oh, and I think only one part of the chain. Okay, so we can't, I need to put in the other, here's this thing right there, and we have a P coming up here, but only one part of the chain has a actual load on it. I think the other part of it doesn't. So we want to find out in this problem they want the maximum principal stress, but probably later on we would want to find, well, let's pretend the thing's made out of cast iron if we get that far. I think if we have that much endurance for listening to all this BS. So like the first thing we would want to do is find out what that FC is going to be as a free body diagram of this thing by itself. Even though this force FC is torsion down right here, this is the force onto C. They really shouldn't draw any forces on here with the two pieces shown, right? Those forces are internal, so it's not right, I think. Many books do that, but I think it's bad because you can only see the force when the parts are separated from each other, right? So that's why I decided to ghost that, so that it says, it's right there. But now, so that force that this thing is going on is combined by a combination of what we could say was going to be, I'll go ahead and call it FCZ, but there's actually, I'm not going to introduce the other naming conventions on this. That's the Y right there. I think this is X and Y. I just started to write Z. So this is looking down that way at the thing. So here's the torque, and if we're going to be technically correct, we'd also have a reaction that way and a reaction this way. drawn on there, but we don't care about those right now. We just want to take the sum of the moments about the, in this case, that is also the x-axis. At least it's down the x-axis. It's x-axis right here. It's down to an axis parallel to the x prime. There we go. So we got that torque, which we know is 100 Newton meters, and it's going counterclockwise. So that's 100, and so minus our FCZ is the only one we care about, and its radius is 0.125 divided by 2. So we're going to get FCZ 100.125 divided by 2. Can do that in my head, didn't want it. Divided by 2, so get 1,600 newtons. So if we want that's supposed to be Y. I think we made noises with my hand just to, so because this is 20 degrees right there, we can find out by taking the 1600 and multiply by the tangent of 20 degrees. So that's 584 newtons. Okay. So we got that's where the force FC is going to be, but in the opposite direction here, right? These are the forces that are on that gear, but now they're going to go the opposite direction for the one that's shown on here. So now we need to get what this P is going to be. So we do another FDD down this thing, but Ghosting goes in because he's behind the thing. FCZ, FCY. There's the shaft, and we'll go ahead and put in the reactions. RY, and here is RZ. And they decided to call it P. I'm not 100% against that, but I can't say I like it. Summation of moments. Now this time it is about the x-axis. So we're going to go clockwise of our 1600, and that's going to be times the radius of this. But truth be told, we could actually just use the diameter and use millimeters, because we're about to do the same thing over here. For this guy, he has, did I even write that somewhere? Oh, no, I did right here. It's 150, right? So plus P times 0.150 divided by 2 equals 0. Whoops. Sorry about that. Home version of the game. So 1600, you just multiply it by 250 and then divide by 150, right? Get the same thing. We get 2,667 newtons. Then we go over to this guy and kind of wish I had left the room, but we'll do what we can. I'll make them a little smaller. Not really making them any smaller. So this is the X, Y plane. This is the X, Z plane. And our forces are, well, we got this guy right here, and he is 22,667 newtons. And we're going to see this little force up here of just 582.4 newtons. Here we don't see anything, but we do have a force right there. We don't see anything on that guy, but this is going to be that main 1600 newtons. So our reactions is going to be our, I think we decided this, these were A, B, C, and D, right? So A, B, C, D. So here's our ray, and that one is also going to be up here. So here's our RDY, and here's going to be our RA. Here's our RAS, and this one's also going to be RDZ, RIDZ. So I think I'm going to do my statics for this little blank little area over here. Some of the moments, and you guys must be tired of this at this point, right? But try not to be too punishing on this. I'm going to write these down in here. I mean, I could just look up. And negative 26 there times our 75. I can just leave it as millimeters. And that's going to be, I guess I should have made it minus up there. I don't do that right now. That 2 is going clockwise, 582.4. 75 plus 250 is 325, I think. And then we're going to go plus R dy, and 325 and 125 is 450. Someone say yes.
Yes.
Thank you. Even if it's not true. Because you told me to.
Extra credit.
That's the teacher's secret weapon. I just made 2 SpongeBob references right now, just for those keeping track. This is Puff in an early episode. X, the teacher's secret weapon. Extra credit. So I'm gonna have to post that now on pop culture. Not as good as SpongeBob's because you told me to. None of it's Patrick because you told me to. In the Olympics and some of the like games right there. Yeah, because Mr. Krabs, do it for the Krusty Krab boy. SpongeBob, for the Krusty Krab. Plankton says, do it because I told you to. Because you told me to. I know. My wife would laugh at it, and now I've mentioned my wife. Every single time. All right, so because I never grew up, I'm still a child, I really enjoy stupid humor. It's really some of the best humor there is, stupid humor. So just because, I don't know, I kind of quasi-made the bed, but I never really ever make the bed, not really to her standards. But I had like a sweatshirt and like pajama bottoms, and so I laid them on the bed as if I was there, right? And then I took one of her pillows and I stuck it like over there as if she had some other thing. And then I just left it. And so she texted me later in the day that she was on the phone with a new client and walked into the bedroom. I started laughing her ass off. Awesome. It was even better that I like kind of sabotaged her career. I don't know. That doesn't sound like the right amount. Did I get that wrong? Yeah. I don't know. I'm not feeling it.
I just did what you told me to.
Because you told me, because you told me to. She would laugh. She would laugh at most things I said. Man. The only person in the world. She gets. Anybody gonna confirm this on me?
Yeah.
Correct. What's that?
It's a SpongeBob reference.
Oh, is it?
Yeah, keep up to date.
But Squidward's like, people yell, so they sound more.
Sounds smarter, like a ghost.
Correct. That's good. Yeah, you know, I'm not doing my SpongeBob justice there. At some point, I just didn't keep up anymore. And the kids grew up. The damn kids, it's their fault. No. That's why your kids you can blame somebody. Is that why?
And they blame you for us.
Oh my God, my kid's so tired of my shit. It's a lot of work to get them to even like acknowledge my existence. They're just jealous I'm funnier than they are. They're hilarious. They take after their mother. So I just wrote into the area that we needed right now. I was thinking that was a nice space to write in, and I'm like, I'm gonna need that here in a second. But okay. RDZ. I really don't want to do this anymore. That's okay. 325 home. 450. Right. So we get 1556 Newton. And then the summation of forces in the z direction equals 0. There. Down is positive. I didn't say what positive was. Yeah. And so we're going to say that we have RAZ minus 1600 plus 1556. Wow, not going to be much. RAZ is 444.4444. So now, we have to erase some of that. Let's hope we got enough room. So, let's see. RAY is 2384. Wow, that's pretty high. So when you subtract out 2, 3, 8, 4, you subtract out 2, 6, 6, 7. You still, oh no, it does go down below, doesn't it? Okay. I was looking at those numbers and there's a little bit of dyslexia there. I mixed my 8 and my 3 in my head there. And then we're going to go down an additional 5, 8, 2.4. So we get a negative 865.1. We should be. Except there's a little bit of round off error. So we're going to come up to here with our 2384 times our, and I want to use Newton meters, so I need to use this as meters. 0.075. So I get a 178.8. And these are Newton meters. Normally I would put it over here what the units were instead of having to put it next to each other. And then We could check this if we want with a 283 times the 250 and track it down here, or we could be lazy and go from the right to the bold, the 865.1 multiplied by 0.125 and be bold. And say that this guy is 108.1. And then over for this one, we have RAZ, which shouldn't that much. He's the 444, 444.
Shouldn't that RAZ be just 44?
Is it for just 44?
I think it's 44.
Is it?
It's a negative 1600 and positive 1556.
Okay, I misread. Thank you. I agree with you there. I was thinking about sponge job. So it's very, very small. And it's the same all the way over. And then we get to the 1600. And so this is pretty substantial right here. And that should be 15, this should be 1556, right? So in this, it's going to go so for this spot, it's going to be real small, 444 or 44.44 times our 0.075, barely going to have anything. We come out to 3.3330. And then for this one, it's going to be 1556 times our 0.125. So he's going to be 194.5 Newton meters. So let's see, this is B and C. So the moment at B is going to be the square root of 178.8 squared plus our pathetic 3.333 squared. So probably not much different than 178.8. Yeah, 178.8 Newton meters. MC square root of 108.1 squared plus 194.5 squared. And we get 222.5. My daughter's calling me. She's trying to FaceTime. She's so pressed. I'm in the middle of class.
I have like questions, so can you just text me?
Yes.
Okay, sounds good.
Love you.
Love you.
So sick of my shit. Okay. So, and this is being recorded, so that's great. So, okay, we need the shaft diameter. Oh, it's a 30 millimeters. We never mentioned that. 30 millimeter shaft diameter. Boom. Anymore. So, we need some geometry. Man, we're filling up this board full of stuff. So, 30 millimeter. me how to do laundry. Why would she ask me of all people? Just, you know, if anyone ever tries to date my daughter, I'm feeling it. Just so you know. Did he really say that out loud? I was just thinking it when it came out. I think I just messed this up too, by the way. I was thinking that and then I messed it up. This is a huge number. That's a crazy number. Okay, 0.03, right?
Tiny number.
Raise the, I meant huge, small.
Okay.
You know, the other kind of huge. Yeah, it's to the minus 8. Yeah, I got it twice. I must be right. 3.9, or I did it wrong twice. Minus 8. That's gonna make it a big for a big number. And J, of course, is 2 times that, or 7.952. So you get the, and we're going to ignore transfer shear because it's on a kind of crazy diagonal plane, and we don't want to bother with that. Maybe I could be cruel one of these days and do that. I don't know. I'll figure it out. No point. So we're going to take that 222.5 and 0.03 divided by 2 and have 3.976 e minus 8. Flip those around. So 222.5 was 0.015 times it. I think I got it. Is that 83.94 megapascals? Man, you can barely see this. I think how bad it would be with the other two. Can't go any further than that, like right there. TR over J. And so we're going to get our torque. Do we ever find the torque? We never found the torque.
Just give it.
Oh, no, that's that torque. We have to find this torque right here. So we need to have, in order to do that, we would actually need a separate free body diagram. Yeah, I know, what a pain in the ass, right? But anyway, we could do either way, but I decided to go with this one. And I went with P, which was 2667. So the internal torque right here. And you might even want to call it torque BC or CB or whatever, because it's between the two things. So that torque is going to be 2667 times 0.075, right? So you get 200. That was exciting. Well, actually, you know, it kind of makes sense. Honestly, this thing's 125, that one's 250. Torque should be half of the thing. And 7.952 e minus 8. So no, 2,200. Flip them over. 0.015 multiplying. So I get like it's 37.73 megapascals. Now we got our stresses. Well, probably get our principal stresses because I did say I was going to do my brittle Coulomb more, right? Why the hell did I say that? I don't know. I was probably feeling more energetic at that point. Oh boy, we're going to go for the tension side of things. So that's our 83.94 megapascals, and I don't care which direction we put the arrow here. for our 37.73 megapascals. This one is going to be a typical uniaxial thing. Sigma A and sigma B. I'm right over here. C is equal to, look how low you go. Look how low can you go? That's usually a game we play. Not in terms of physically, but how disgusting can you be? Sailor type of thing. And what I really found useful when I went out to sea is that my first roommate had one of the most disgusting minds I've ever met in my entire life. I mean, this guy, you couldn't believe how low that guy could go. So when I went out to sea and they tried to embarrass me by saying very disgusting things. Lower. One lower. It's a skill set. That's something to be proud of. Not something you brag to your mother about. Hey, Ma, look how awful my mouth is.
Yeah, I don't get that.
Yeah, actually even worse for me. All right, so sigma A, I'm really making a mess of this thing. You can tell I'm tired. Maybe a little tired. 41.97 and 56.44. Probably made a math there somewhere. 98.41. And then sigma B, C minus R. We're going to end up with 56.44 and 41.97 to be a negative 14.47. We're going to use our brittle Coulomb norm. We haven't picked out a material yet, but we know that we're going to use sigma A over the ultimate tensile minus sigma B over the ultimate compression. Just remember that that minus is only there because we're going to have compressive sigma B, not because we would actually subtract the two things. So let's go and look up the only brittle material that we have available to us in table A24 is the gray cast iron. And let's pick something. We're going to reverse engineer this that would actually work. Well, taking a look at the information available to us, we can kind of tell that only one of them is really going to be anything greater than 1, right? The 60. Because all the tensils are less than the tensile stress we have. So let's take a look at the gray 60. Which has an ultimate tension of 62.5 and an ultimate compression of 187.5. So you can really see from this that the compression is not really going to even factor in much, right? Because I only have 14.47 compared to that. It's going to really dwarf the comparison of our. Well, no, we're going to make it anyway. I was deceived. Yeah, that was way too large anyway. It's already. We can't make it. Right? It's not going to work with it, but we can still figure out what they're going to be. You can plug the numbers in yourself. Let's see. I'll do it up here. We'll erase 187.5. Let's flip them over. And 62.5 divide plus I get BMC, I mean BCM, little coulomb more of 0.061. Can't make that shaft out of cast iron. That's not a good candidate for your cast iron shaft. With all those opportunities for mistakes, I wonder how close we got. How close? How far? I wonder if my computer's still working here. That's here. So we go to books. Nope, it's froze. Nothing. Won't even let me change. Oh well. I'll take care of that when I get back to my office. All right, yay! Is it still recording, you think? Oh, nope, stopped recording. No, it's still recording. It says still recording. It says stop recording, so it must be still recording. Turn me. I don't know when you said that, Jemai, but I bet it was definitely relevant at the moment. All right, so I think we're done. There's a lot of exam prep stuff to go through and to look over, right? And I will set the solutions so that they show up on Sunday. Is that what I said?
Yes.
So let me make sure I do that. Let me say Sunday at noon. Sure. So spend all tomorrow doing these problems. No, that's probably not going to happen. But I'm going to do my dynamics review tomorrow. You guys are welcome to come. Sure, we'll do that, right? Just you know, to make yourself feel better, you guys are much more prepared than any single student in my dynamics classes for the exam. But I'm going to do something about that. We're going to fix that all tomorrow. It's all going to come together.
I want to see the one for the brief.
Okay, cool. Sorry about that. You too.
Thank you.
You're welcome. Sure, sure. I'm going to stop recording. That's it. I'll put it right back to my just a second.